Spacecrafts landing on Earth is routine. Yet why is it landing on Mars is so difficult that it's known as the 7 minutes of terror?
One of the things that makes physics beautiful is how vast its scope is, still founded on the same universal laws. From tiniest particles to orbiting planets, no matter where you are, these laws never change, only the conditions under which they act do. What lights up my love for physics is the thrill of understanding how these unchanging laws express themselves in different environments.
And nowhere is it more challenging than in EDL or entry, descent, or landing.
This is the phase by which a spacecraft travels through an atmosphere and reaches the surface safely.
NASA describes this as one of the most challenging parts of any mission.
On Earth, the atmosphere is our friend. Its high atmospheric density provides strong aerodynamic drag, which helps us naturally slow down an aircraft until parachutes or controlled landings can take over.
This is described by the drag force equation. It tells us that drag is directly proportional to atmospheric density. Since Earth's atmosphere has a higher density, this results in a greater drag force, making landings relatively manageable. Mars, however, is a different case.
A spacecraft enters the Martian atmosphere at hypersonic speed and has only about 7 minutes to slow down. Mars' atmosphere is only about 1% as dense as Earth's, which results in a weaker drag force. Yet, it is still thick enough to cause extreme heating. Even thin air, when compressed at high speeds, converts kinetic energy into thermal energy,
raising heat-shield temperatures beyond 1800 degrees Celsius.
This leaves us with a paradox. Mars's atmosphere is too thin to slow you down, yet still thick enough to try and burn you up. As a result, as spacecraft descend, parachute must be deployed while airflow is still supersonic, a behavior so unstable that engineers use CFD, computational fluid dynamics, to simulate shock waves around the fabric.
Even after parachutes, it still isn't enough. Curiosity and Perseverance used rockets and skycranes to cancel their remaining velocity, applying Newton's second law of motion, F equals to ma, in bringing the spacecraft to a complete stop.
As exploration pushes further into the solar system and beyond, physics becomes our guide through extreme and unfamiliar environments. Understanding how the same laws behave in different atmospheres lets us learn how to explore not just Mars, but any world we may one day reach.
And this knowledge does not just stay in space. The physics developed to survive Mars improves our understanding of Earth's atmosphere.
The same equations that explain heating during planetary entry describe heat transfer in aircraft and energy systems. The same fluid dynamics that predict shockwaves and turbulence on Mars help us model airflow as well as better understand weather and climate here on Earth.
Physics reveals a universe ruled by simple, unchanging laws. And by testing them in space, we learn to use them more wisely here at home.